chemical equilibrium. We're going to talk about solving equilibrium problems, steps to do that. Quote of the day from Mark Twain, Life on the Mississippi. Here's a practice problem for equilibrium problems. This reaction here, we're given the following information at 35 degrees Celsius. Here's our experimental data. We need to calculate Q and state which direction will the reaction proceed to reach equilibrium. So our formula here for Q, products over reactants raised to their coefficient powers. So here's how to set it up. You plug in the numbers given in the problem. Q sub C equals 1.0 times 10 to the negative 8. Great, right? How many of you got that answer? Did you get it? Unfortunately, that is not the answer. Read the problem carefully. Look at what you have. What do you have? You have the moles. You don't have the molarity. Okay? Brackets mean concentration of. All of those equilibrium expressions require concentrations, not moles. Concentration, moles per liter. So divide them, get the initial molarities, then plug in the numbers, and you get your Q value, 5 times 10 to the negative 9. Q is less than K sub C, therefore the reaction will shift to the right in favor of products in order to reach equilibrium. So it has to shift to the right based on the Q value. When you want to predict the reaction direction, first thing you want to do is balance the equation. Second thing is write the equilibrium expression. Now, is it possible to write the equilibrium expression if you haven't balanced the equation? No, you don't have the power to write. List the initial concentration. So you just want to know what you start with if you're given that information. Then you calculate the Q, determine the shift in equilibrium. So here's how to go about problem. You make an ice table, that's right. Boom, 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 boom. Ice, ice, baby. That's right, ice tables. Ice tables are your savior, they're great, they're fabulous. First thing you want to do is you make the table, you've got your initial concentrations, you define the equilibrium concentrations, and then you substitute the equilibrium concentrations into the equilibrium expression and solve. So table, define, substitute, you're done. Last rule, number 8, is if the initial concentration is greater than 100 times K, you assume the initial concentration plus or minus X is equal to the initial concentration to simplify the algebra. So this is a step we'll look at with these practice problems. And then validating step 8 by the 5% rule check, and we'll get into this in more detail as we go. So here's a sample problem. We've got an equilibrium at a particular temperature. We've got the value of K. We've got the initial concentrations of Br2 here and the Br concentration here. So you're asked to calculate the concentration of these species at equilibrium. So to calculate the concentrations of these species at equilibrium, what's the first step we need to do? Okay, first step, balanced equation. Is it balanced? Yes, it is. Next step is write our equilibrium constant, equilibrium expression. Third step here is choose a variable. Let X be the change in concentration of the Br2. So here's our Br2 going to 2Br. The initial molarities are given to us. So there's our initial 0.063 and our final 0.012. So as you're reading the problem, write down the equation, write the initial. Then we're going to see how much it changes. Molarity changes. In this case, let's X be the change in concentration of Br2. So you're losing Br2, it's forming the 2Br. You're gaining 2Br because of this coefficient here. So losing X of these and gaining 2X of those in the process. Then at equilibrium, you just add these up. 0.063 minus X and 0.012 plus 2X. This is called an ice table. Initial change equilibrium. So you've created a nice table for the problem. Okay, your K can be written with the products over the reactants. So the products are here, the reactants are here, raised to their coefficient power. Okay, then to calculate your value, you plug in the numbers you have. So for the Br concentration, that's over here. that goes in here squared. And then this goes down here, of course. It's not squared because it has no coefficient. So that calculates at your k value of 1.1 times 10 to the negative third. Now you just need to solve the equation for x. So using some algebra, we multiply it out. Here we've got the equation equal to 0. This is of the format here. Ax squared plus bx plus c equals 0. So we've got a quadratic equation to solve this problem. So we solve the quadratic equation, x equals that value, or x equals this value. So got a little bit of a challenge to it because it's a quadratic equation. At equilibrium, the concentration of Br2 here is this value. And so if you plug in your x for it, it could be 0.009 negative molarity. The question is, can you have a negative molarity? Or it's this value here. So if you look at these two, which one is more likely to happen in reality? Is it a negative molarity or a positive molarity? So the second one gives you the value with a positive molarity. So with that value there, at equilibrium here, you've got the Br concentration is there, and then the Br2 concentration is this here. So you use that same x again and plug it in here. Now, this is a complicated process because of the quadratic equation. Once you get past that, it just has to make sense at equilibrium. Sample problem 2, got hydrogen and iodine making HI. Is it balanced? Yes, it is. So, next step, you move on, create your initial concentrations. Here's your equation, initial concentrations. What goes next? That's right, change. So you say minus x is the, again, you assume x is the change in H, hydrogen and iodine, and then plus 2x, according to the mole ratio. And your equilibrium, add them up, add them up, add them up. Kc, plug them in, there's your Kc values, and your value is 54.3. Where did the 54.3 come from? There it is in the problem, so that's where that 54.3 came from. Solve for x. Here's your solving for x. X equals 0.393 molarity. However, that's not the final answer. What are we looking to do? Let's calculate the concentrations of all species at equilibrium. X is none of the species, right? But you have to plug it in to get your final answers. So that's not your final answer, so then you plug it in and get your final answers of hydrogen iodide and hydrogen iodide. And those are your final answers there. Here, if we look at these, we have initial concentrations, example problem 3. What do we do first? Equation, initial, change, equilibrium. So, in this case here, these are all initial concentrations, okay, here, and it says calculate the concentration of all species at equilibrium. So, for this here, it says first calculate the Q to determine the reaction direction. In this case here, when you plug in these values, again, these are the initial concentrations. You're using the previous information in the previous problem to check that. The Q value is less than the K value. Because of this, the reaction is going to proceed to the right. So, if we look at this, our initial, our change, minus x, it's going to the right, of course, plus 2x. Equilibrium, plug in our values there, and we have our Kc. We're solving again using the K constant to find out the equilibrium. So we've got two possible options here in this particular equation. The question is, which one do we use? Do we use use 0.0114 molarity or 0.001156 molarity. Two choices, both positive, neither one's negative, you can't rule one out. So here, if we use the 0.00156 molarity, we get our concentrations. So we got a little bit of a challenge here. Equilibrium systems where k is greater than 1 requires a quadratic equation. So one is favoring the products. When k is much, much less than 1, when k is less than 1, then you have a system where you can assume that the initial concentration of A minus X is going to equal the initial concentration of A because X is super small, very small. Okay, so if k is much, much less than 1, this is assuming the x value is going to be the small part. If k is much greater than 1, this favors the products. The products is going to be larger. K is less than 1, it's going to mean that the reactance is larger, not due to the x, but due to the A sub 0. So it does not require the quadratic equation if you can make this assumption where k is much, much less than 1. Problems with small k, you can assume the initial concentration minus x is equal to the initial concentration because the change in x is so small. A 5% rule, as long as x over the initial concentration of A times 100% is less than 5%, that this assumption works. Again, if it is not less than 5%, you would not want to make this assumption. You would use the quadratic equation. So then this assumption is valid and the quadratic equation is not needed. So for 5%, use quadratic. So here we have a concentration, calculate the equilibrium concentration of all species at 25 degrees Celsius. And there's our constant. So ice, initial concentrations. Okay, what about the change? All right, so if we look at our k value is incredibly small, right? Pretty small. Less than 1 for sure, but pretty small. So for our change, okay, we're losing HF, gaining H, gaining F minus, equilibrium. And so now we've got our setup here. So that's set up just like the other problems. So you can use the quadratic equation or we simplify it. So we check our rule, 100 times the K. Okay, is it less than 0.5? So we can make the assumption here. If we make that assumption, then X is 0.019 molarity before moving on. So if this is making the assumption and then moving on, we check the validity. So we do our X 0.019 over the 0.5, which is the initial concentration of A times 100 equals 3.8%. So is it valid? Yes, it's valid. We can move on. So we use those in that 0.019 to get our calculated values. Makes the problem a lot easier in terms of the math side. No quadratic. That's cool. However, if it's greater than 5%, you know, 555, must use a quadratic equation. No way around it. Worst case scenario, okay? You got two options. You got quadratic, you got an assumption, less than 5% works. Worst case scenario here. We got a reaction. 2NOCl, 22NO plus Cl2. K is small number, less than 1, 1.6 times 10 to the negative fifth. We got 1.2 moles of NOCl, 0.45 moles of NO, and 0.87 moles of Cl2 are mixed in a 1 liter container. So, first thing we need to do is find the equilibrium concentrations. That's right. Can't use moles in the K value. So, initial. 1.2, does that work? It works for moles, but not concentrations. Okay, so let's choose X to be small. NO will be the limiting reactant. Choose NO to be X. So the final amount you're going to get, NO is, again, the limiting reactant. Figure out the change in NO. Change equals the final minus the initial. So it's X minus 0.45. This is called an ICF table. A little bit different. That gives us our initial change final. At final state, it will be at equilibrium, so that's our ice table. So now we've got our x minus 0.45. So that's going to be the change that's going to happen based on equilibrium. Now you figure out the other changes. So if you get x of NO, what's the Cl2 going to be? Use stoichiometry. Cl2 is half the change in NO. And then NaCl is minus the change in NO. So now we can determine the final concentration. So we got 0.45 minus x, because it's plus x on this side. So we got our minus x, we got our plus x, and we got our 0.5x based on the ratios. So then we can, oh, there we go, look at that. Determine the final concentration. So we do the initial minus the change. And we get here, we get our 1.65 minus x and our 0.545. So this gives us, at equilibrium, we've got our x here to start with. It usually starts with this. It depends on how much it changes here. Now we can write the equilibrium constant. So we've got x squared over 0.5x plus 0.645 over 1.6 minus x squared. Now we can test our assumption x is small. Ignore it in plus and minus. So to test our assumption, if we ignore it in plus and minus, x equals 8.2 times 10 to the negative third. This helps us figure out our final concentrations, 1.64, 0.649 for Cl2, and we can check that assumption. So our 0.0082 divided by 0.649 is 1.2%. That is okay. So again, we solved for our x value, 8.2 times 10 to the negative third, and then tested it out, assuming it was right, and then checking the percentages here, 1.2%, that's okay. Here's a sample AP exam question. Hydrofluoric acid dissociated in water, equilibrium constant expression, and then molar concentration of H3O in this molarity. The first step we do is our equilibrium expression, okay, and then we plug in the values here, assuming x is much, much less than 0.40, and we've got x squared over 0.40, rearrange it, x squared 0.40 times the value, x is equal to 0.017 molarity. Here's a sample of uranium oxide placed in the flask, chlorine gas is added, and here's the reaction. So the first thing is write the K expression, equilibrium constant. I want to do that now if you can. Okay, next part of this problem, after you do that, there's your constant. Again, it's all based on pressures. So the pressures are all given in the equilibrium constant. Now, the next question would be, calculate the partial pressure of O2 at equilibrium at 862. So here it gives us the data about the partial pressures of the chlorine gas and uranium oxide chloride, dichloride gas here. So calculate the value of Kp for the system. At a certain period of time, 1 mole of O2 is added, and does the mass of the U3O8 in the flask increase, decrease, or remain the same? So one thing you want to notice is this here is a solid, hence it's not included in the equilibrium. Gas, gas, gas. So this is a homogeneous gaseous equilibrium, although it's got solid in it, it doesn't affect equilibrium. So heterogeneous equilibrium because it's got the solid in it as well. So here's a sample problem. You can work on this. Let's check our answer when you're done. Pause the video. Here's our ice table, how to solve the problem. Part B, here's our K expression once we have the concentrations here. At a certain period of time, 1 mole of O2 is added to the mixture in the flask. Does the mass increase, decrease, or remain the same? So we add O2 to it. What's it going to do about the equilibrium position? Mass of U3O8 will increase because the reaction is at equilibrium. And the addition of a product, we added a product here, will cause a stress on the right side. The reaction will proceed from the right to the left to reestablish equilibrium so that some O2 is consumed as more of this and this are produced. And that concentration will go down. So that's how to explain answer to F. This chemistry is put in place in the Haber process, nitrogen and hydrogen making ammonia, and with a exothermic 92.6 kilojoules per mole produced in the reaction. The mole percent of NH3 versus pressure, you can see the relationship. Getting it up to 100%, you need a large amount of pressure. Okay? The more percent you have with the temperature, it affects the concentration of products, NH3, and the reactants, N2 and H2. So the challenge is you've got hydrogen and nitrogen. Okay? You have to compress them and get them to react. Okay? This forms ammonia, but it needs to be condensed into liquid ammonia. As the liquid ammonia is removed, this H2 and N2 return back into the system, so you're adding more hydrogen and nitrogen. Okay? As you remove the ammonia, more ammonia is going to form. Remove this, it's going to shift to the right. However, if you try to remove as much as possible and then take the hydrogen and nitrogen out. When you take the hydrogen and nitrogen out and you remove these, the equilibrium will shift to the left, and you can get this unreacted H2 and N2 back into the compressor for the next reaction. So you've got two competing processes happening, making the ammonia, and when you remove it, it makes more ammonia. And then when you remove the H2 and N2, it makes more H2 and N2. So the ammonia that doesn't condense becomes unreacted H2 and N2 as you remove those two. So it's a way of keeping track of everything so you don't have any ammonia going back through the unreacted compressor, or very little. You will maybe get some, but it will be at equilibrium, of course. Chemistry in action as well, life at high altitudes and hemoglobin production. Hemoglobin is an equilibrium system with oxygen. The oxygen fits into the hemoglobin molecule, and that oxygen fits in. However, when you add more concentration of oxygen, as you add the oxygen here to this side, it shifts the equilibrium here to the right. It makes this hemoglobin complex where it's holding the oxygen. If you remove the oxygen, it shifts it towards the left, and so you're going to have less oxygen that can travel around the blood and get to your cells, and more separate oxygen with hemoglobin. So when you breathe in oxygen, it's an equilibrium system with hemoglobin being produced. So it takes time for your body to reach this equilibrium where your cells are used to the amount of oxygen going into them. And this is why your hemoglobin can adjust over time. It takes a few weeks to adjust to high altitudes. And this is why sports play at higher altitude. One of the reasons why there's less oxygen going to the athlete is because of this equilibrium system is being shifted or stressed to Le Chatelier's principle. This is a widget you can look at for reversible reactions. It's pretty cool. It shows some of the reactions, and you may look at this in class as well as we're working on problems. So tomorrow in class, please bring in the following things. We'll be focusing on equilibrium problems number 1, and then you can also again, bring in, take a picture of whatever you need to do for your textbook. Bring in these problems. We'll be working on those tomorrow in class. Have a good night. I'll see you tomorrow. Just in case you need more help. Another practice problem. Try it out. See if you can do it. Don't look at me.